Mastering Pandas, Installation and Environment Setup. Welcome to your journey into intermediate Pandas. In this lesson, you will install and verify Pandas, set up Jupyter for hands-on coding, load real-world datasets, begin to explore the tools for powerful data analysis. Running the cell now. After this overview, let us try checking your Python and Pandas tools together. Let us make sure everything is set up right. We will check your Python version and see if Pandas is installed. Here we comment our intent. We import the system library to get Python details. This prints your Python version. The Python version appears below. We import pkg_resources to list the installed Python packages. Import numpy as np. We set the random seed to 42 for reproducibility. This line quickly makes an alphabetical list of packages you have. We check if Pandas is in your list. If this prints true, Pandas is ready. If not, we will install it next. Running the cell now. This output confirms that you are running Python version 3.12.1 and that the Pandas library is successfully installed in your environment, which is essential for starting your data analysis work. Notably, it also warns about the deprecation of the pkg_resources package, indicating that future code might require updated methods to check installed packages. This step ensures your setup is ready before diving deeper into Pandas functionality. If Pandas is not found, do not worry. Let us install it in the next step. If Pandas did not show up above, let us install it now. This cell checks and installs Pandas automatically inside your Jupyter environment. We describe what this cell will do. We import system so we can run system commands from Python. We import subprocess to actually run those commands. We assign the package name we want as a string. We use try to safely check if Pandas is available. If Pandas is installed, we celebrate and print a confirmation. If Pandas is missing, Python will try the next block. We let users know installation is starting. Here we upgrade pip first, to avoid problems. Now we install Pandas using pip, the Python package manager. We confirm in the notebook when the install is complete. Running the cell now. This output confirms that Pandas is already installed in your environment, so no installation was necessary. This verification step ensures you have the library ready to use for your data analysis tasks, aligning perfectly with the lesson's goal of setting up your Pandas environment. Try rerunning the previous check cell if you had to install Pandas. Next, you want your code output to stay neat while working. Let us set Pandas up and clear out annoying warnings. Here we comment about what the next lines do. We import the warnings module to control warning messages. This command will silence future warning pop-ups in the notebook. We import Pandas and shorten its name to PD. Now, PD stands for Pandas everywhere below. Let us check exactly what version of Pandas we have. Running the cell now. This output confirms that Pandas version 2.3.0 is successfully installed and ready for use. Verifying the version ensures your environment is correctly set up to follow along with the lesson's upcoming intermediate Pandas techniques. If you see a version number printed, Pandas is ready for any analysis. How to launch Jupyter for hands-on data science. If you are not running this in Jupyter yet, open your terminal or Anaconda prompt. Run Jupyter Notebook. This will launch a web interface in your browser. You will write and run code in these interactive cells. Running the cell now. Practice, open a terminal and try typing Jupyter Notebook, then come back when your browser opens. It helps to have real data in front of you. Let us load the famous Titanic survival dataset. This cell comments that we will load data for Titanic. We import Pandas. Short as PD so it is easy to use. We copy the data link for Titanic from an open GitHub source. We load the spreadsheet with all Titanic rows into a data frame. A data frame is a table-like structure for your data. Here we check how many rows and columns the dataset has in total. This line gives you a sneak peek at the first 3 rows, so you see exactly what is inside. Running the cell now. This output confirms the Titanic dataset has 891 rows and 12 columns, showing sample passenger data including survival status, class, and demographics. Notice how the code loads the data and prints its shape and first 3 records, establishing a foundation for exploring and analyzing this dataset in Jupyter. This step ensures your environment is correctly set up to begin hands-on data science work. Take a moment to look at the column names and the shape before moving on. Exploring a data frame in Pandas. Now you are holding a real table of survivors and passengers. Let us explore the Titanic data so you know what you are working with. What columns do you see? How many rows are there? How might this data be useful to predict survival? Running the cell now. Try naming 3 columns you see, and think about what information they hold. When you load a new dataset, always ask, what types of data do I have, and how clean is it? Let us explore quickly. We add a comment to state our purpose to summarize. This method shows column types and missing data counts. You will know which columns are numbers or text, and where information might be missing. This prints quick descriptive stats for all number columns. Things like average, minute, max, and counts. This helps you spot ranges and possible problems. Running the cell now. This output shows the overall structure and summary statistics of the Titanic data frame, highlighting that there are 891 passengers and 12 columns. Notice key details like missing values in the age and cabin columns, which you'll need to handle later, and the survived column where about 38% survived. This initial exploration helps you understand the dataset's shape, data types, and completeness before proceeding with analysis. Practice, which column looks most interesting to you so far? Sometimes you want a quick feel for the categories or values inside a single column. Let us try it with sex and passenger class here. We explain here that our code previews 1 column at a time. This line shows all unique categories for sex in the data. Categories are text labels like male or female. This shows how many passengers are in each passenger class, helping you learn about ticket types. Running the cell now. Here we see that the sex column contains only 2 unique values, male and female, confirming it's a categorical feature with 2 groups. The SP class O column shows the distribution of passengers across classes, with most in 3rd class, 491, fewer in 1st, 216, and 2nd, 184. This quick summary helps us understand the composition of the dataset before deeper analysis. Try changing column names to explore different columns, for practice. A lot of datasets in real life have empty or missing values. Let us check which columns are missing data, and practice cleaning out empty ages so analyses are not thrown off. We start by stating that we will check for missing data. This command prints how many values are missing, by column. High numbers tell you where to look first. Now we use dropner to remove rows where age is missing. This helps us focus on passengers with age data. We print how many rows remain after cleaning. Running the cell now. The output shows the count of missing values in each column, revealing that aged has 177 missing entries and a cabin A has the most with 687. After dropping rows where age is missing, the data frame now contains 714 rows, ensuring we only analyze passengers with known ages. This step is crucial for accurate age-based analysis in the Titanic dataset. Try running df.isnl.sum again to be sure age is clean now. Creating new columns based on existing data is called feature engineering. Let us build an age group column to help analysis. We explain that this cell will make a new column based on ages. We use pandas.cut to put each passenger into an age group. We set bins and group names, so small children, teens, and adults each have a clear label. This prints out both the age and the new age group columns, so you can see if people are grouped as expected. Running the cell now. Here, we see how the continuous age values are categorized into meaningful age groups using bins, which help simplify analysis by grouping similar ages together. Notice the new age group who column assigns each passenger to categories like young adult and the adult, making it easier to spot trends by age category in later steps. This demonstrates how pandas can create categorical variables from numerical data, a key step in data exploration. Try using value_counts on age group to see the distribution. Filtering means picking out rows that meet certain rules. Let us see just adult women in the Titanic data. We begin by saying this cell does filtering. We use Boolean logic to pick only those who are female and at least 18 years old. This prints out a preview of the filtered result, letting you check a few rows. Running the cell now. This output shows the first 3 rows of the filtered data frame containing only adult females, demonstrating how to use conditional filtering in pandas. Notice that the age values are all 18 or older and the sex column is consistently female, confirming the filter worked as intended. This helps you focus your analysis on a specific subgroup within the Titanic dataset. Try changing conditions to select adult men or teens for practice. Now you will learn group by. This lets you analyze data for each group or category one at a time. Let us see if survival rates change by age group. We start with a comment about grouping. We use pandas.groupB to collect people by age group. We then take the mean, which shows us the survival rate for each group. Printing this shows each group and its average survival rate, which is actually the percentage of survivors by group. Running the cell now. This output shows the average survival rate for each age group in the Titanic dataset, revealing how survival chances varied by age. Notice that children had the highest survival rate, 58%, while seniors had the lowest, 34%, highlighting how the Group B operation helps uncover important patterns in the data. This step is key to understanding the structure and trends within our data frame. Practice. Can you try grouping by sex instead to compare? Joining and merging lets you bring new data in. Here you will add a simple calculation for family size, then join it to the main Titanic table. Here we explain what we are doing, creating a new table for family sizes. First, we copy names and the SIB-SP and PARCH columns. SIB-SP is number of siblings and spouses, PARCH is parents and children traveling together. We sum up the two with 1 for the person themselves to get each passenger's family size. Now we merge the new family size back into the main data frame, matching on name. How left keeps all original rows. Printing a sample lets you see the new family size column attached. Running the cell now. Here we see the first 3 rows of the data frame after adding a new family size column, which sums siblings to spouses, SIB-SP, and parents, children, PARCH, plus the passenger themselves. Notice how the merge successfully aligned the family sizes back to each passenger by name, revealing small family groups, typically 1 to 2 people here. This helps us understand passenger relationships and household sizes on the Titanic, a key step in exploring the dataset. Try finding the largest family size value with max. Pivot tables mix grouping, summarizing, and reshaping powerfully. Let us see how survival varied by both class and gender. We start by describing that we are using a pivot table. We create a table with passenger class as rows, sex as columns, and the survival rate in each cell. AgFunc takes the average, so our rates are easy to read. This prints the result. You can easily compare men and women by ticket class. Running the cell now. This pivot table shows the average survival rate by passenger class, P class, and sex, revealing key trends in the Titanic dataset. Notice how females across all classes had significantly higher survival rates than males, particularly in first and second class, which helps us understand how social factors influence survival odds. This output demonstrates how pivot tables can summarize complex data to highlight important patterns quickly. Changed survived at fair to explore other pivot possibilities. Time series is about analyzing data over time. Here you will load a flight's dataset and see a simple monthly trend plot. We comment our purpose, to show a time series. We import Seaborn, which has many built-in datasets. We load the flight's dataset with monthly passenger totals. We group by month and sum the total passengers flown in each month across years. Here we plot a line chart. This makes trends over time easy to spot. Running the cell now. Here, we group the flight's data by month and sum the passengers to see overall travel trends throughout the year. The line plot shows how passenger counts vary month to month, revealing seasonal patterns. This step illustrates how grouping and aggregation help us summarize data before visualizing key trends. Try plotting by year instead of month for a different view. Pandas works well with Matplotlib and other plotting libraries. Let us quickly make a bar chart showing survival by sex. We start by explaining we are going to plot data. Here we import Matplotlib so we can customize and display our plots. We group by sex and get the mean for survival, then plot a bar chart with nice colors to help compare the two groups. Adding a label to the y-axis so it is clear what the bars show. We title the chart for clarity. This displays the plot below your code cell. Running the cell now. This bar chart shows the average survival rate for each sex in the Titanic dataset, making it clear that females had a higher proportion of survivors than males. Notice the height difference between the bars, which reflects this key trend in the data. This visualization helps us quickly grasp survival disparities by sex, fulfilling our goal to explore and understand important columns in the data frame. Try making a similar plot by class, or with a different color scheme. Let us practice exploratory data analysis, EDA. This is where you ask key summary questions about your dataset. Here we comment that these lines do quick EDA. We check if survivors paid more for tickets, using Group B and mean. How does age differ by class? We take the median age by P class. We announce we will now check the ports where people got on. We count how many people boarded at each port. The dropner argument shows missing values too. Running the cell now. This output reveals key summaries of the Titanic data, showing that survivors paid a higher average fare than non-survivors, indicating a possible link between fare and survival. The median age decreases with passenger class, reflecting different demographics across classes. Finally, the embarkation counts indicate most passengers boarded at Southampton, with a few missing values, helping you understand distribution and data completeness for these important columns. Try a question of your own next, such as average family size by survival. Let us continue the project with new feature engineering and looking for patterns with correlations. This will help you spot possible predictors of survival. We comment our plan, engineer a new feature and check correlation. Here we create a new column showing the fare divided by the number of family members, an estimate of how much each person paid for the trip. We print a sample of the new column for a quick check. Now we set up to look at correlations with the survived column. This command shows you a correlation grid which reveals how closely different columns are related. Numbers close to 1 or -1 mean strong relationships. Running the cell now. Here we created a new feature, fare per person, by dividing the total fare by family size, helping us understand the cost burden per individual. The printed output shows the first few rows with this new column, highlighting how fares are shared within families. The correlation matrix then reveals relationships between survival and key features, showing that higher fare and slightly larger family size have weak positive correlations with survival, which hints at potential predictive value. Try creating your own new features and running a similar correlation test. Pandas has helpful options for cleaner output and quickly working with large data. Here are a couple of tips for smooth workflows. We mentioned that these are tips for better performance and display. Set maximum columns to see more of your data frame at once. Can help when columns get cut off. Take a random sample of 100 rows to speed up previews and avoid scrolling too much. This prints a quick sample of your subset data. Running the cell now. This output shows a random sample of 3 passengers from the Titanic dataset, revealing key columns like passenger ID, survived, P class, age, and fare. Notice the variety in survival status, class, age groups, and family size, which helps you start understanding the data's structure and diversity. This snapshot confirms the data frame holds rich, mixed-type information ready for further analysis. Practice, try taking different sample sizes for exploration. Everyone sees errors sometimes. Let us practice a common one, a typo. The code tries to access a column that is not there. How might you fix it? This line is a comment explaining the topic, common Pandas errors and how to fix them. Start a try block to attempt running code that may produce an error. Print the first few rows of the column named fake column in the data frame df. If an error occurs, catch the exception and assign it to the variable e. Print the error message converted to a string to show what went wrong. Give a helpful tip, check spelling or use df.columns to find valid column names. Running the cell now. This output shows how Pandas handles an attempt to access a non-existent column, producing a clear error message. The lesson here is to always verify your column names using df.columns to avoid such errors when exploring your Titanic data frame. This helps ensure smooth data manipulation and prevents common mistakes early on. Practice, try typing a real column name to see the error go away. Let us try an interactive challenge. You pick an age group and see the first names and their survival status. This is a comment explaining the challenge theme. This line asks the user to input an age group to filter by. This line filters the data frame to only rows that match the chosen age group. This line prints the first few rows of the filtered data showing name, age, and survived columns. Running the cell now. Here we see the first few passengers filtered by the chosen age group, showing their names, ages, and survival status. Notice the mix of survivors, 1, and non-survivors, 0, which helps you understand the data's structure and what kind of details are available for each person. This step is key to practicing how to filter and inspect subsets of the Titanic dataset based on criteria you select. Try this with several groups to explore differences. Quick recap. You have installed Pandas, loaded a real dataset, and practiced data cleaning, transforming, group B, joining, pivoting, and visualization. You even explored basic error handling and user interaction. With these core tools, you are ready to go further in data science. Running the cell now. What next? Practice building your own notebooks with different datasets and ask your own questions. If you like this, remember to like, subscribe, and leave a comment. See you in the next Pandas adventure. Running the cell now.